Welcome to The Explainer. Today we're going to pull back the curtain on some of the most incredible engineering on the planet, the science hidden inside the world's largest moving objects.
You see them out on the horizon, right? These absolute titans of transport. But how often do we actually stop and think about the insane challenges they're built to handle, day in and day out?
And get this, around 90%, that's 90, of all global trade travels by sea. I mean, our entire modern world literally depends on these things. The fuel in your car, the food on your plate. Chances are it spent some time on one of these steel giants.
So what's the secret sauce? What's the invisible science that keeps these colossal steel giants afloat, upright, and plowing through some of the most powerful forces on Earth? All right, let's dive into this amazing battle of human ingenuity versus raw nature.
Okay, so first things first. A modern ship, it's not just a big boat. Not even close. It's a ridiculously engineered system. You should really think of it as a collection of really, really hard problems. And for each one, there's a brilliant solution.
So what's challenge number one? Well, it's the most basic one of all. Just staying upright. I mean, a ship is out there in a totally chaotic, sometimes violent sea. It's being pushed, rolled, lifted. So how in the world does it stay right side up?
Well, it all starts with a tug-of-war between two powerful forces. First, you've got the center of gravity. Just imagine all the ship's weight, the steel, the cargo, all those engines, all of it focused on one single point. And that point is always pulling the ship straight down.
And then, fighting right back, you have the center of buoyancy. This is the balancing point for that huge upward push from the water. Archimedes' principle. It's basically this single point where the ocean is pushing the ship up.
Okay, so here's where the magic happens. When a wave rolls the ship, right, the shape of the hull that's underwater changes. And when that happens, the center of buoyancy actually moves. This creates this incredible invisible lever between those 2 points, gravity pulling down, buoyancy pushing up, and that lever literally pulls the ship back upright. It's this constant self-correcting dance between the ship and the sea.
And that right there, that constant dynamic balancing act, that's the real secret to a ship's stability. It's not about being rigid and stiff. No way. It's designed to be responsive, to restore its own balance with every single wave that hits it.
All right, so the ship can stay upright, awesome. But that just brings us to the next massive problem. How on earth do you push something that big? We're talking hundreds of thousands of tons through something as thick and heavy as water, and do it efficiently.
Well, designers are basically fighting a war against two kinds of drag. The first is what you'd expect, frictional resistance. It's pretty much just the stickiness of water clinging to the hull. But the real villain, the true energy hog, is wave-making resistance. That's the enormous amount of energy you waste just making waves as you plow through the water.
And the solution to that is, well, it's this thing. This weird-looking nose you see in the front of pretty much every big ship. It's called a bulbous bow, and it is an absolutely brilliant piece of engineering that honestly seems like it shouldn't work at all.
So how does it work? It's so cool. The bulb itself creates its own little wave out in front of the ship, and it's designed so that this little wave is perfectly out of sync with the main wave coming off the bow. So what happens? The two waves basically cancel each other out. It's like noise-canceling headphones, but for water. This slashes the drag and can save up to 15% on fuel. That is a huge deal on a trip across the ocean.
Okay, so our ship is stable, and it's slicing through the water efficiently. We're good, right? Nope. That brings us to challenge number 3. See, a ship at sea isn't just floating peacefully. It's in a constant battle, being bent and twisted by unbelievable forces that are literally trying to rip it in half.
The trick here is to stop thinking of it as a boat and start thinking of it as one gigantic hollow steel beam, a girder. Because as it moves over waves, sometimes the middle of the ship is on a wave crest with the ends hanging in the air, and sometimes the two ends are on waves and the middle is sagging in a trough. The bending forces are just staggering. Imagine thousands of cars worth of weight trying to snap the ship like a twig.
So to survive that, the design has to be perfect. Naval architects have to calculate exactly how all the weight is spread out, factor in the buoyancy force that's pushing up differently along the hull with every single wave, and then figure out all the resulting stresses, the shear forces, the bending moments along the entire length of the ship. It's an insane puzzle.
And this is where material science becomes just as important as the shape of the ship. You can't just use any old steel. They use specialized, high-tensile steels, stuff that's way stronger and more flexible, in the spots that take the biggest beating, like the main deck and the very bottom of the hull.
But, all this amazing engineering costs money. A lot of money. And that brings us to the final and maybe the most important challenge, the business of a ship. Let's be real, a ship isn't just a cool piece of tech, it's a massive financial investment. And if it's not profitable, it simply doesn't get built.
And breaking down that cost is a puzzle in itself. You can see here huge chunks of the budget go to just the raw steel, the giant engines, all the labor to put it together, plus massive overhead for the shipyard. Literally every single design decision has a dollar sign attached to it.
And, on top of that, you're investing this huge sum of money in a market that is famously, well, crazy. Just look at this index. The price to build a new ship goes through these wild boom and bust cycles. It can literally double or get cut in half in just a couple of years. So deciding when to build is a massive financial gamble. The economic pressure never stops. Here's a great example. The fuel a ship burns goes up with the cube of its speed. What does that mean? It means if you double your speed, you burn 8 times the fuel. 8 times. That's why a huge part of the design is calculating an optimal speed, that perfect sweet spot, where the money you make from getting there faster is balanced against that insane fuel bill.
So you take all these challenges we've talked about, staying stable, being efficient, being strong enough, and making a profit, and now they're all being looked at through a totally new lens. The game is changing. It's not just about conquering the sea anymore.
The naval architects of today, they're facing a whole new wave of problems. Now they have to design ships that meet really strict global efficiency standards. They have to figure out how to use new, cleaner fuels like LNG or maybe even ammonia. And more, they have to think about sustainability for the ship's entire life. We're talking a 40-year lifespan, from the first piece of steel all the way to recycling.
And that really leaves us with a huge question, doesn't it? As all this technology moves forward, is the biggest challenge still going to be conquering the sea, or is it going to be protecting it? That question, it's right at the heart of naval architecture today. And the answer is going to shape not just our global economy, but the future health of our oceans themselves.